time wait for no man. So it's 8 o'clock sharp. So we're gonna jump straight into it. I'll start off with a very quick introduction. As some of you, this might be your very first time attending our online revision session, or that you are not even familiar with OVERMUGGED itself. So let me begin with sharing a bit more about myself first. I'm Daryl. I mainly only teach chemistry and physics. In fact, I only teach Sec 4s. So I've been teaching for quite a while, over a decade now. And a lot of times I'm happy to flex that my students generally do quite well. Much credits to them, as much credits to myself. But I would say that really the secret here is that if you're in my class or in any of our group tuition, you would know the secret is very simple. We just work really hard and consistently. So every single week there's homework, we'll go through. When it's closer to prelims, we'll do a lot of prelim papers, mock exams, practical. So there's really no secret to doing well. So for the rest of you who might not be in my class, that's completely fine. But just understand that in general, there's just no shortcut to success. If any tuition teacher tells you, oh, you join my class straight away, you get A1, that's nonsense, right? Because you do need to put in the work and the hours to make it happen. But I'll say that consistency is usually the thing that we typically neglect. So if you want to get serious and you think that, hey, I want to do well for my O levels, physics, or even for any subject for that matter, just remember you have to be consistent. All right. Fun fact about myself is I can't drink milk. So that's kind of sad because when we get bubble tea, I can't even drink it. But such is life, lah. Right. Now, for those of you who are new to the OVERMUGGED brand, we are across 8 branches in Singapore. So earlier I was mentioning I mainly teach at Kovan in Jurong East, but of course there are other tutors located at our different branches. So if you need help anytime, just hit us up. Anyway, the first lesson is a free trial. And we are very proud to sort of like, show off that our students always do very well. But as I was sharing earlier, it's really not any crazy secret. It's just about being consistent. And the very fact that you're here today for this online revision shows me something, which is that you do care about doing well, right? Because if you are one of those students that go like, screw this, not important, it's just WA, you won't even be here. So my promise to you is that if you have committed and you have sacrificed your Monday night and to spend it with me to do physics, I promise you that this session will be productive, that you will learn something. How much you learn depends on how well you're able to absorb whatever I'm saying. All right. So I want you guys to really stay focused from the start to the finish because I just have so much that I want to share with you guys, especially for these 2 chapters that are predominantly always tested in WA2. All right. Now, in terms of resources, later on you'll see me referencing some of this, but I will be going over to the curated notes quite a bit. So if you have a copy of this because you are already in our group tuition or you have purchased a copy online, I think it'll be quite helpful to look at some of this. Now, for the rest of you without the curated notes, don't be too worried because you can still use your textbook or your school notes. It might look a little different, but I'll say that the content roughly is there. It's just that the curated note is a bit more concise, straight to the point with some work examples. But you should still be able to follow the lesson irregardless. All right. And of course, if you are in our regular classes, you will get a lot more preparation. In fact, we also do hands-on practical because we realize that that's one of the areas that is sorely lacking when it comes to exam performance. All right. But other than that, I don't want to really go on too much further because we are here to do physics today. So let's jump straight into it. I'll only be covering 2 chapters. The reason why these 2 chapters are selected is simple because this will be regularly tested in your WA2. Now, I'm going to begin by first talking about what we need to learn in this chapter in DC circuits. For those of you who are very confused, like, what the hell is this page? This page is what we call your learning outcomes. Meaning at the end of the chapter, once we are done with the content, going through the questions, all of this, you should know what it means. Now, if I can categorize for you broad strokes what DC circuits require you to know, firstly, you need to know and you need to be very familiar with circuit diagrams. So, the chapter is literally called DC circuit, right? So you need to be able to look at a circuit, understand how you interpret it. And I'll say the key thing here is that you need to be very clear in terms of dealing with a series circuit versus a parallel circuit. So almost entirely of the first part, right, is about getting familiar with series, parallel, and to look across the different components and the different formulas, like if I can put it that way. You need to know how to look at your potential difference, your current, and your resistance. Most of you should have an inkling of what I'm saying already. But the most important part is I want you to focus on part E. It's not so much about the formulas. right? A lot of it you'll see nowadays, the change in the syllabus as to how schools and MOE is testing you is the ability to apply the principle to new situations and solve related problems. Apply to new situations, solve problems. Apply to new situations and solve problems. This is why earlier I alluded to this concept of, hey, if you're just going to be memorizing formulas, it is really hard to do well for physics because it's never about the formulas and the definitions. It's about learning a concept and then applying it, right? So you'll find that today we'll be spending a lot of time in the application process, right? To apply to solve certain questions, right? And I'll say if you are very clear on this, you'll find that, hey, this chapter is never about the formulas, but it's about solving questions. Of course, there will be important concepts like the potential divider, which we will go through. You'll also see your thermistor and your light-dependent resistors. Once again, you'll be required to solve simple questions. So if I break it up into two halves, series parallel, let's solve questions. Second half, potential dividers, you will see thermistor and your light-dependent resistor. Okay, for the notes itself, just simply download it on the Telegram channel. All right, let's jump straight in. Now, this page itself is probably the most important page of them all, which summarizes what we need to know about this chapter. Now, I'm going to go through this real quick because most of you have clarified in the chat that you have already learned this chapter. Now, when we're talking about a series circuit, what I need you to know is that the current would flow throughout as though it is one main river. So it means that irregardless of whichever point in the circuit, they will all share the same current. The difference, however, for a parallel circuit is that the parallel circuit, will split up into individual branches. Okay, sorry, having difficulty with the highlighting. Okay, you know what? Never mind, let me change this up. You will split up your current into many different branches. So how I usually like my students to visualize is think of this as a river. Is your river one continuous river, or does it split up into smaller rivers? So the difference between series and parallel is just the fact that the current will split. Nothing more than that. Next, for potential difference, in series, you need to know that whatever EMF you are given will be divided across the components. Most straightforward, let me just give you an example. This is 6 volt. This will be 3 volt plus 3 volt. So in a series circuit, you simply add up the potential difference. Meanwhile, for a parallel circuit, if this is 3 volt, every single branch will receive 3 volt. So this is sort of like the rule that governs it. So if you think about it, current is equal throughout in series, but potential difference is equal across each branch. In a parallel circuit, you need to add up the individual branches to get the total current. In voltage in series, you need to add up the individual potential difference to get the EMF. So that's sort of the rule, and our job is to apply this to different situations. Next, for resistance, we simply add them up, but for parallel circuits, we need to add the reciprocal. So later, I'll show you how to do the working and the breakdown, but this more or less governs the first half, which is, do you know your series and parallel? All right. Now, as I've said earlier, say easy lah, right? But when it comes to solving questions, that is when it gets complex. So for those of you who have yet to download this, please go to the Telegram channel to download the Physics Sec 4 WA2. This worksheet consists of 15 MCQ, and we're going to jump right in. All right. So I'll be toggling between the blank version, which is what you see over here, as well as my annotated version. So I already prepared everything beforehand, but I don't want you all to just see the answer right away. I want you all to have a chance to try alongside me, because I think what's more important is not the answer, but the thought process towards getting the answer. So let's take a look at question 1. We have a circuit, and we were told that the resistance of the circuit can vary between 2 to 4. Now, what is the maximum effective resistance? So the question is guiding us to think. Now, the arrangement is fixed. I can't change the arrangement, but I get to choose. Do my resistor have 2 ohm or 4 ohm? In this particular arrangement, how do I get the maximum resistance? Now, don't overcomplicate things. If you want the resistance to be as high as possible, there is no reason absolutely for us to use the lower end. Even if you place it in parallel, to get a higher overall resistance, it is way better for us to use the higher tail end. So this means this question is, in other words, getting us to solve the total resistance when this is my exact distribution. Now, when we approach such a situation, this circuit is not exactly series, it's also not exactly parallel, right? So how should we approach it? I always advise we simplify. In other words, what I want you guys to do is to first simplify this segment. These two are clearly in parallel. So what we're going to do is to find the resistance of this parallel segment, after which you then add in the 4 ohm. So in short, we try to convert this parallel into the total, like the final amount before we add the 4 ohm in. So how would the working look like? Okay, this is how the working will look like. Don't worry about the answers because I will review it once we're done with the MCQ, but I don't want you all to be over reliant on the answer. So this 4 ohm over here is the one in series, but I'm saying that for this one over here, I want you all to calculate it out. Now, for those of you who are a little confused about what's going on here, let me elaborate. So the formula for calculating resistance of a parallel circuit is 1 over R equals to 1 over R1 plus 1 over R2. There's no R3 because there's only 2 of them in parallel. So 1 over R in this case is 1 over 4 ohm plus 1 over 4 ohm. But in order for us to express our answer much quicker, so it's about efficiency here, we know that we need to flip this 1 over R to find the R value. In other words, we will use the term reciprocal. So from here, if you want to find R, you need to take this entire expression to the power of -1. So that's why you see over here, my working is just simply what's in the bracket to the power of -1. Now, if you're extremely confused with this, maybe because your math is not strong whatsoever, doesn't matter. You can simply solve this the traditional way as well. What do I mean? It means that 1 over R equals to 1 over 2. Please, 1/4 plus 1/4 is half, all right? And then you simply flip it around, R equals to 2 ohm. Also can, there's nothing wrong. But when I write it like that, with the power of -1, this entire thing also gives me 2 ohm. So 4 ohm plus 2 ohm gives me 6 ohm. This is my maximum effective resistance. Clear? The question can simply change. How do you get the minimum effective resistance? Instead of using 444, you'll use 222. But remember, you always simplify the parallel part first before you add up the total resistance. This question, sadly to say, is considered easy. All right, so I won't dwell too long on this. I just need you guys to understand at the end of the day, your calculation steps needs to be displayed clearly. Even though it's MCQ, but imagine if this is structured, you probably need to be able to show your working. All right, if not, let's move on to question 2 next. Okay, this question I'll say is difficult. Now, for those of you who had the chance to do it first, I hope you had a chance to try, but I'm assuming most of you also don't have the time, right? This is probably your first time looking at the circuit. So let me just give you a very quick 30 seconds to try to look through this question, think about it to see if you're able to get the answer. True, right? I think most of you haven't done it, right? Cannot be you're so enthusiastic, go and download and do first. Impossible, man. Okay, so how does closing switch S change things? Not easy, right, this question? Why not just give it a try? If you think you have the answer, can you all type it in the chat? If it's wrong, then wrong lah. Nobody cares. Nobody will remember your answer anyway. But let me see in the chat what you guys think. Just an A, B, C, D. Okay, let's see what you have. Don't need to shy, you can just type it into the all chat. I don't think anybody cares, but let's see what answers you'll get. So far, I already got B, C, and D already. Okay, keep it coming. The rest want to give it a try. Okay, I see a couple of you actually getting a hang of it, that you guys were able to get the answer. But for me, what is more important is, yes, you get the answer, but are you able to justify it confidently? Now, let me run straight into this question. Okay, and especially those who do not know how to solve it, listen up. Now, the first thing is to address what really happens when switch S closes. So if switch S is closed, I need you to understand that instead of passing through both R and Q, closing switch S will cause what we consider a short circuit or the establishment of a shortcut. Now imagine your current flowing through. Follow the pink path here. I can choose now, do I go through R or do I go through S? You need to recognize that S is a path of no resistance. So if such a path exists, everybody will take this shortcut. And hence we call this a short circuit. So now you see that the current, instead of passing through both R and Q, closing switch S means I can bypass R, meaning now my current only passes Q. Now, having the ability to skip one resistor tells me that the total resistance of my circuit will drop. Why? It's as though we remove one component, right? With lesser components, resistance is bound to drop. And the relationship between resistance and current is that if R decreases, your current goes up. So now the total current in the circuit has increased. So the current flowing through L, which is the total current having increased, will be brighter. So I don't think many of us should struggle with getting the conclusion that L is brighter because total resistance drop, current increases. Now, the part that I think whereby some of us might be a bit more hesitant is what happens to P. Now, I've written down the full explanation. I want you guys to follow the chain of thought. In the past, current does split at the yellow point. It splits to go through P, and some of it will go through R and Q. Now, the key difference now is that after we close the switch, more current would flow through Q as resistance has decreased. Now, we need to go one step back to revisit, right, our understanding of current and resistance. What does this mean? You need to understand the relationship between the two. In the past, this branch, I'm referring to the R plus Q, resistance is high. So it's only going to draw a small current. But with the removal of R through the shortcut, my total resistance in this branch has dropped, which means more current would flow through this path compared to before. So if more current is going to flow through Q, there'll be less current that flows through P, which explains why P will be dimmer. One more time, the original pathway got R and Q. The new pathway only has Q. With less current, with less resistance, more current. So if more current goes to Q, there's less current going through P. So P would be dimmer. Clear? So the current that goes through P and Q, when it adds up, it goes through L. So the total has increased. But now the amount of current that flows through P is lesser than before. Why? Because more current has been diverted to go through Q, since resistance has dropped. This is what I mean by understanding. Even if we modify the circuit and change it up a little, you guys are still able to apply it to new situations. Focus on this, don't focus on the formulas. All right, so that's question 2 for you. Fun fact, I set it one more time in the later half. So if you couldn't solve it here, you'll try it again later on. If not, let's move on to question 3. Okay, now question 3 itself will be a big nightmare for a lot of us. Why? Because the moment you see this sliding contact moving, I think generally most of us have a bit of PTSD. But like, oh shit. Furthermore, all right, I think it's a very scary word for some of us when we see the term potential divider. So I'm not going to generalize to say that, oh, everybody cannot do this. I think some of you probably can. But I think most of you will agree that these are the kind of questions that you are more worried about. Now, earlier when I was talking about what you need to learn about this chapter, I've mentioned that the potential divider is a very important concept. So let's spend some time to revisit the concept of potential divider. All right, my students, you should know what's coming. All right, but for students that I don't teach directly in our regular classes, let me run through with you how to divider. Oh no, it's hanging. Oh dear, am I back? Sorry, I think there was a bit of a lag, right? Can you let me know if I'm alive? My laptop low-key hanged for a while. You all type in the chat if you all can hear me. Can? Okay, perfect. Sorry for the disruption. Let's go. Okay, so I'm scrolling to the part of the notes, right, where it covers potential divider. But my own students, you guys would know this, that I absolutely hate it. I hate the formula with a burning passion. So in general, I always say that screw the formula. Formula is not important. But the question here is, do you know what is potential divider? So let me explain it in 1 minute. Potential divider, let's flip the word around, divide the potential difference. What this means is that if your battery is 6 volt, this 6 volt will need to be split between R1 and R2. Hypothetically speaking, if R1 has a resistance of 2 ohm and R2 has a resistance of 4 ohm, this 6 volt needs to be split in the exact ratio in terms of the resistance ratio. So you can see here the 6 volt, how you'll end up splitting is a ratio of 2:4 or 1:2, doesn't really matter. This one receives 2 volt, this one receives 4 volt. Divide the potential. So how does my 6 volt get split? You got lesser resistance, you receive lesser voltage. You got more resistance, you receive more voltage. Of course, these numbers can change. So let's try another set of numbers. So maybe you make it slightly more challenging if you put it that way. So let's say the resistance here is 10 ohm, right? And the resistance here, let's say it is 30 ohm, right? Less harder, right? Okay. So what's the ratio here between R1 and R2? Is 1:3. So without even having to apply any formula, my 6 volt must be split in a ratio of 1:3. If your math is good, 1.5 volt, 4.5 volt. Because this 6 volt needs to be split in a ratio of 1:3. So what exactly is potential divider? Look at the resistance, split your voltage up accordingly. It's just a ratio. So there's truly no need to worry or to think too hard about the formula because the formula is just helping you to calculate a ratio. All right. So if you actually could understand what I'm trying to say here, right, then I think the easy part here is, hey, 6 volt, I just need to split it between the two. As long as they get it according to the ratio, it's fine. I can keep changing up the resistance numbers. You'll get different voltage split. But at the end of the day, this is literally what potential divider is about. So if your school taught you differently or it looks more complicated than it is not. Which is why all of my students, when we go through in class, remember, we say, screw the formula. Let's forget about it. Let's understand potential divider. Because the moment you understand how it works, the ability to apply to different situations then occurs. If you only memorize the formula, you can't solve anything and it's pointless. Clear? All right. Now, let's immediately apply it to a question and let's see if we can actually get this question right. This question is pretty long, but let's run through the key points. We have this sliding thing that can move from P to Q. It's about 1 meter long and the resistance is 30 ohm as indicated in the question. We have a potential divider and this is my thermistor. Resistance of the thermistor can vary from 10 to 90, right? So thermistor is like variable. Later on, we will talk about it in detail, but the changing of temperature will change the resistance. Now, we were told that the temperature of the thermistor is high. Now, what does that mean? Now, even though we haven't covered this in detail, most of you have already learned a chapter and should know that if the temperature of the thermistor is high, this means that your resistance is low. All right, so between the 10 and the 90, you should be using the 10 ohm. Fair enough? Okay, now, without focusing too much on the question for now, I want you all to look at the EMF. This is 12 volt. My 12 volt needs to split between 30 ohm and 10 ohm of a ratio of 3:1. So without doing too much, let's ignore the question first. Let's just apply the concept of potential divider. So how do I break up this 12 volt to split between the 30 and the 10? Question, how much should the 10 ohm receive? Can anybody help me in the chat and type up the correct answer? So if it's 1:3, how do I split up my 12 volt? How much should my 10 ohm receive? Okay, 10, 3, 30. 1:3. How do I split 12 volt between a ratio of 1:3? Exactly. You guys got it. This will be 3 volt. Right? And the 30 ohm will be receiving 9 volt in the ratio of 1:3. This is literally all potential divider is. So if you find this, wow, why is it so easy? It's because it is really that easy. It's just whether do you learn it the right way. Okay, but this question is not all, because there is one component here whereby it's saying that the slider is moving from P to Q. Now, what does this mean? If you want to find out the potential difference at P, you are essentially measuring, hey, there is no resistance here. So how much should my voltage be? It will be 0 volt. But if you actually have the wire slide all the way to Q, it is then measuring the entire potential difference across the whole resistance wire. So what this means, right, is this. Let me go over to the annotated version. At P, right, you are essentially saying that you are using 0 ohm. If you slide it all the way to Q, you are 30 ohm. So let's take a look at how your reading will look like. If initially your slider was at position P with 0 ohm, you are splitting 12 volt between the 10 ohm in the thermistor and the 0 ohm. So of course, all of the voltage will go to the 10 ohm, and the reading for your XY would be 0. But if you slide it all the way to Q, you're using the entirety of that 30 ohm, which means now your 12 volt will split between the 30 and the 10. So how much would a 30 ohm receive in terms of the potential difference? It will receive 9 volt. So how would your reading change? Initially at P, you'll be 0 volt. But when you slide it all the way to Q and you use the full 30 ohm, the split will get you 9 volt. So that's why as you slide it from P to Q, the voltage will change. So there's two concepts in this one question. Firstly, do you know how to do your potential divider? Secondly, do you understand how the sliding contact changes the resistance of the wire that is being measured? Fair enough. Easy, not the easiest, but I hope you guys can learn from this question. All right, because I feel like this question type is usually where when we say DC circuits, we're a bit scared, right? This kind of questions. But I would say, as long as you break it down step by step, definitely doable. Okay, let's move on. Okay, next up, question 4. We now approach thermistor and our light-dependent resistor. My own students, you guys already know what I'm going to tell you. So just give me a chance to share it with the rest. Okay, so for me, right, as a teacher, I really hate getting my students to memorize. So usually if there's a fact that we need to know for certainty, there's usually either a story or analogy. So I want to just share with you guys the one that I always use when it comes to memorizing our LDR and thermistor. Okay, so for those of you who do not know me, all right, I recently got married, all right, and this means before I get married, I obviously had to propose, right, to my girlfriend. And as I was debating, hey, which are the places that I can propose to her, I asked my bros for some advice. Typically the bros will give you good ideas. So one bro told me, hey, why not you go and Halloween horror night and you propose to her? I'm like, what the hell, right? Like seriously, who would propose during Halloween horror night? Such a bad idea. Another one told me, hey, you go Sentosa, the beach, during sunset, go and propose. Of course, that would be a lot better. So how can we use this scenario to remember how does thermistor and LDR work? So imagine I did my proposal in a cold and dark cave or Halloween horror night in a haunted house. Do you think she's gonna say yes? Do you think my girlfriend's gonna say, oh yeah, I'll marry you? She'll be like, what the hell, right? Take photos also so ugly. The resistance is very high. If I propose, then she probably says no, right? Resistance is very high. But imagine I had some sense, right? I did it at the beach. Okay, this is not me, by the way, but I just photo. Like if I did it at the beach, right, when it's bright and sunny and hot, and then it's like very romantically asked, oh, will you marry me? The resistance gonna be very low. She's gonna be like, oh, so cute, all right, so nice. She'll probably say yes. Okay, so what do I want you guys to remember from this example? It is cold and dark. resistance is high. When it's hot and bright, resistance is low. So earlier, I think there was one question in the chat, which is, shouldn't the temperature increase means resistance increase? No, because if temperature increase, I go to the beach, resistance is low. So I like to use these examples to try to remember this because this is hard to forget. And I'm quite certain that for most of you who remember this example, you can very easily come back to this and remember the proposal and to think from the girl's POV, would resistance be high or low? It's low-key impossible to forget. Instead of memorizing such facts, it's a lot easier to put a story or a picture to the whole thing. All right, now let's apply this exact scenario to the question. Which condition gives the smallest resistance? Should I propose in the cold and dark cave or at the beach? Which one have a smaller resistance? The beach, right? So the beach is hot and the lighting is good. Lighting is bright. So hot and bright. Fair enough? Ken? Okay, as for the question, why does the thermistor work this way? There are different types of thermistor. The one in our syllabus is what we call the NTC thermistor. Therefore, it works in such a way whereby if the temperature increases, the resistance will drop. There's another kind of thermistor that's not in our syllabus. So in order not to confuse you guys, I'm just going to stick with there's one kind of thermistor, at least at O levels. Clear? All right, so I hope that there's no doubt there. Okay, next up, question 5. We are looking at this scenario. We are trying to ensure that the LDR's potential difference is the largest. Now, if you haven't gotten the notion yet, the most common way potential divider is tested is with LDR and thermistor. They love to combine these two concepts together in one single situation. So the question will look something like what you see on screen. Let's recall how a potential divider is meant to work. We have the EMF. The EMF is supposed to split between the components. The higher the resistance, the more the voltage. The lower the resistance, the less the voltage. So we're trying to create a situation whereby the LDR gets a lot of voltage, right? The light-dependent resistor, I want voltage to be as much as possible. This means that that means I need my LDR to have super high resistance, right? Because in terms of ratio, if you want your V to be high, your R needs to be high. But at the same time, if I want most of the voltage to go to the LDR, this means I want as little voltage to go to the thermistor as possible. This means I need to create a situation where my thermistor's resistance is as low as possible. Because a lower resistance here results in a smaller voltage. LDR, I want the resistance to be high so that I get more voltage. So the appropriate condition is that if I want LDR to have high resistance, LDR high resistance, dark or bright? Cold and dark cave, right? So I have a dark situation for my LDR. But I want my thermistor's resistance to be low. So I should use hot. Hence, a dark and hot situation will cause the potential difference to split in such a way whereby my LDR receives most of the voltage. Okay, this is not a question asking you, hey, how do I ensure both have high resistance or both have low resistance? If that's the way you're thinking about it, it means your understanding of potential divider is not there. Potential divider means I have a fixed cake, right? It's like a one pie. But how do I slice up the pie? I need to give a lot to the LDR, very little to the thermistor. So I need to configure their resistance to be of that. You get what I mean? So it's not about both must have high resistance or both must be low. It's not the case. All right, so that's all for question 5. Moving on. Okay, this one I think is quite easy. I think most of you actually do have a hang of this. The main thing that you need to remember here is that if you're trying to use a voltmeter, voltmeter is always connected in parallel. Now, what do I mean that you'll be connected in parallel? It means that you'll be testing for the potential difference before and after. But instead of talking about, hey, it is supposed to be connected in parallel, let's take a moment to take a step back. Why is it connected in parallel? Okay, now we need to understand the behavior of current first. Now, as a current, right, as I come out from the battery, I will travel to this point. At this very juncture, I have two choices. I can either go through my resistor or I can go through my voltmeter. Now remember this, If you want your voltmeter to be ideal, meaning it's the perfect voltmeter, you do not want any current to flow through the voltmeter. Why? If current really flows through the voltmeter, that means there is less current that's flowing through your resistor. In other words, your voltmeter is as though it is disrupting the whole thing, right? It's supposed to be there, but not be felt. It's just there to measure the potential difference. I don't want it to change my current flow. I don't want it to actually affect my circuit. So in order for me to keep the circuit going, ideally I want all of that current to flow through my resistor, as though the route to the voltmeter doesn't exist. So in order to achieve that, in order to make sure that no current ever flows through the voltmeter, we can ensure that by making sure that your resistance is very high. Because if the resistance is like infinite, right, current can never pass through. So all the current is then forced to pass through the resistor. So at the end of the day here, it's not about memorizing, oh, it's in parallel, resistance is very high, but you probably can understand why. So in order to make sure that all my current flows through the resistor, my voltmeter resistance must be super high. Now, if you're clear on this logic, right, let's apply the same thought process to the ammeter, which is placed on the main circuit itself in series, meaning the current actually flow through the ammeter. So in order to ensure that the ammeter measures current and yet it doesn't affect anything, we need our ammeter's resistance to be super low. In fact, so low that as though it is not there, that my current will pass through as per normal. So voltmeter's resistance is very high, but ammeter resistance is very low. The same thing can be therefore understood why the voltmeter is in parallel and the ammeter can actually be on the main circuit itself in series. Okay, one analogy that I always go back to is to think of your ammeter as though it is the ERP on the roads, right? So, I mean, you guys probably know what the ERP is. When a car passes through, right, it charges something, right? Like what, $2 for passing through the gantry and stuff. But the ERP is there, but it actually doesn't slow down the cars. The cars pass through as per normal. So think of it as the ammeter as something that's counting how many cars are passing through per second, right? It doesn't slow down the car. It has zero resistance, but it's there to measure the rate of flow, right? In circuits, it's the rate of flow of charges. Meanwhile, in the roads, the ERP is the rate of flow of cars, right? So the ERP doesn't have any resistance. Meanwhile, the voltmeter here has super high resistance to ensure that it doesn't affect the current, that all the current goes through the resistor as intended. Clear? So no memorizing, we built for understanding. I'll keep moving on. Okay, this one, especially for those of you who didn't get it right earlier, let's think through one more time. What is the logic? What happens to bulb J? If we close the switch, bypass P, right? Overall resistance drop, J will be brighter. What about bulb K? If I'm allowed to bypass P, the resistance here decreases. So if the resistance in the second branch decrease, the current will increase. So if more current flows through this second branch, less current would flow through K, making K dimmer than before. So this is almost identical to the previous question, all right? But I think it serves as a very good pit stop to double check. Have you truly understood your stuff? Clear? I simply changed the naming for the light bulbs. Right, so I hope most of you are following. I won't dwell too long on this since I already went through. Let's move on. Next up, question 8. I'll show all of the MCQ answers once and for all at the end. But let's go through what we need to know here first. Okay, next up, we were told, hey, which switches needs to be closed for the two lamps to be operating at normal brightness? Now, I think the key thing here is understanding what normal brightness means. Normal brightness means both light bulbs get sufficient voltage. Now, in case you have forgotten, one of the first things we have discussed today was that the EMF of the battery, which is 12 volt, this EMF will be equal across each branch. Meaning if you are parallel branch, every single branch will receive 12 volt, 12 volt. Now, the key thing here is this. The first branch is quite straightforward. There's only one light bulb. So this branch is 12 volt. All 12 volt will go to this single light bulb, allowing this light bulb to be operating at normal brightness at 12 volt. However, the second branch potentially can have up to 2 light bulbs. If you allow current to flow through both light bulbs, meaning you close P, you open Q, you close R and S, meaning you close P, R, S, current will flow through both light bulbs in the second branch. This means even though this branch gets 12 volt, the 12 volt will be divided equally to be 6 volt, 6 volt. Because potential divider, we need to split that 12 volt between the two light bulbs. This is not ideal because this means that both lamps will not be operating at normal brightness. So instead, your goal is to make sure that only one light bulb is in play. To do so, you need to close switch Q, which allow us to bypass the first light bulb so that all of the entire 12 volt intended for this branch goes to this single light bulb between R and S instead. So this allows two lamps to be operating at normal brightness. If you also have this other light bulb here, then it's 6, then that is no longer normal brightness. So this is how you approach question 8. All right, if not, moving on. Remember, if you have questions, you can ask. Okay, next. The questions here wrap up the DC circuits part. Next up, I'd like to talk a bit about the practical electricity question types. Okay, for practical electricity, I think most of us will have this view on it, which is that it's quite easy. I wouldn't say no. I do think it's easy, but there's a few parts that I'd like to address here. Now, what goes into this chapter? The very first part requires us to be familiar with the formula, which I'll break down later for you, and the ability to calculate the cost of electricity using kilowatt per hour. The second part is about the hazards of electricity, as well as all of this, which is the safety. Right? So if it's dangerous, how do we keep ourselves safe? So the second part is really about the dangers and the safety elements. Now, I want to talk very quickly about the main formula that you learn in this chapter, which is that power equals to voltage times current. Now, if you are taking pure physics, I highly recommend that you also study the second and the third formula. Right? So if you're only taking combined, I will argue actually P equals to VI is good enough. But if you're taking pure, very likely you will need the second and the third. Now, of course, you can just memorize the formulas. In fact, it is not that difficult. But let's spend a very short moment to understand why is the second and third formula called derived formulas. Now, the first formula that you learn is P equals to VI. This is the new formula that you learn in this chapter. I'll break it down for you later. Why is it like that? Actually, you know what? Let me break it down for you now. Why is it like that? Okay. Now, P equals to VI. How do we go about getting this formula? Power equals to V. Now, what is V? If you actually know your chapter well, voltage is actually energy per charge. You learn this in the chapter, current electricity. Current is charge over time. If you look at the way this is being arranged, you can easily cancel out Q, and you can see that P equals to E over T. Power equals to energy over time. So it is true that power can be found by taking voltage times current. That part in blue is not so important. It's just to let you know that this formula is legit, all right? Because sometimes teachers don't bother to explain, right? But very quickly, this is the back-end reasoning why power can be found by taking voltage times current. But what is more important for me is to also acknowledge that in the chapter in current electricity, we also learn the formula V equals to IR, whereby voltage can be found by taking current times resistance. Now, why is this formula important? It's because we're going to attempt to sub in this formula here. What I mean is, instead of writing P equals to VI, we let V be equals to I times R. Meaning we say V is instead I times R multiplied by I. And this is how you get I squared R. So power can be found by taking current squared times resistance. If you manage to read this part, you probably know what's going on next, which means that I can also sub in I. I equals to V over R. Can follow, right? Current equals to voltage divided by resistance. So if I sub it in, how does it look? Power equals to V multiplied by current. Current is V over R. So V times V over R equals to V squared over R. This is how you get your second and third formula. It's like simultaneous equation or just subbing in, whatever you call it. All right. But I hope you guys don't look at these two formulas from now on and feel very intimidated. Why? Because you're just subbing in another formula that you already know anyway. All right. But I think this pretty much encapsulates the first part in terms of making sure that you guys are clear on which are the formulas that are important to you in practical electricity and how they are derived. I find a lot more importance in the explanation why than just to blindly apply that. Okay, with that being said, let's move on and take a look at the very first practical electricity question. Now, question 9 focuses on the danger, right? So over here, we see that the wires have not been connected properly. We see that the live wire, there are parts that are sticking out, and some parts of this live wire actually touches the neutral wire. Can you see this part here? The neutral wire, this part. I highlight. Until you cannot see. I'm talking about the thing. Can you see this line here? This is the neutral wire. So the live wire touches the neutral wire. What is the consequence? Now, normally, if there wasn't such a situation, the current will come in via the live wire at high voltage, pass through the light bulb, and return via the neutral wire. But in the case of what we consider a short circuit, whereby the live wire touches the neutral wire directly, now we have a shortcut. We have a path of no resistance. This means that the current will bypass the component. It will not pass through the light bulb. And when that happens, your resistance will decrease, right? Because you're no longer passing through the light bulb. You're passing through this new path with no resistance. And typically when that happens, as the resistance drops, your current will spike, right? Because there's no resistance, your current will just shoot up. And that moment will lead to the fuse melting. So if your live wire ever touches your neutral wire, it creates a short circuit, current greatly increases, that will cause your fuse to blow. I always emphasize this to my students, which is that everybody knows how a fuse works. When current is too large, the fuse will blow. But the difficulty here is that, do you all know the situations that leads to the fuse blowing, right? That's a lot more important because that sets context. Why does the fuse blow? Everybody knows why. But what is the situation that leads to the current suddenly spiking, right? And I'm telling you right now, if there's ever a short circuit situation, the current will spike. And that will cause your fuse to melt. The second most common situation that will cause that to happen is if your earth wire is activated, which I'll talk about later on, right? So in ever any case, right, whereby your earth wire comes into play, you expect your fuse to blow as well. Clear? All right, so this is for question 9. Okay, why are the others not accepted? Let's take a quick look. I think that's a fair question. Earth wire will divert the high current to the ground. Earth wire will only divert the high current to the ground if live wire touches metal casing. So your earth wire will strictly only come into play if the live wire touches the metal casing. Okay, why? Because your earth wire is connected to the metal casing. So in this situation, your live wire touches the neutral. It didn't touch the metal casing. Okay, but if it does, then option B will be the answer. Okay, C is the same thing. If you have the earth wire being activated, this is only if the live wire touches the metal casing. So I'll say that both situations here is provided if live wire touches metal casing. Okay, now neutral wire will divert the high current to the ground. This is not true. It is anything, the moment you see the word ground, diverted to the ground is always done by the earth wire. What the neutral wire does is to bring the current back to the socket. The neutral wire is not associated to the ground at any point. Earth wire is associated to the ground, right? Like earth, ground, right? Can? Okay, all right. So that's all as to why the remaining options are wrong. Okay, it's not that B and C are not true. B and C are true only if the situation is if live wire touches metal casing. Okay, moving on. Thanks for the questions, by the way. Okay, this is the one that I want to talk about as well. Okay, this we see the plugging is wrong because the green and yellow wire, which is the earth wire should have been connected to the top one, right? So the pin on top is actually the earth wire. But you see here that the earth wire instead is connected directly to the part with the fuse. If you ever see fuse, right, this tells you where the live wire is. Okay, anyway, the live wire is brown. So what happens if the earth wire touches the live instead? So if earth wire is touching the live, earth wire which is connected to the metal casing is now at high voltage. This results in a situation that, hey, since the earth wire is connected to the metal casing and the earth wire is at high voltage, indirectly we are saying that the metal casing is now at high voltage. So as a human, if I go and touch this metal casing, I will get electrocuted. Okay, so the casing becomes live. But take note that the toaster should continue to work. Why? Because the current is still going in via the live and coming out via the neutral. The whole thing can still work. There is no change in the current flow at all. However, now with the wrong wiring, you are now saying that my appliance, there's extra wire that connects to the metal casing, and we are bringing a very high voltage and current to the metal casing. So as a human, if I touch it, I become part of that circuit, I will become electrocuted. Okay, so just remember here, these are all dangers that we're trying to understand why. So remember, earth wire, metal casing. If earth wire is at high voltage, metal casing is also at high voltage. Okay, next, let's move on. Another very common question type that you will definitely see are question types that focuses on the calculation of electricity consumption. In short, your focus is to get kilowatt per hour. For those of you who are very confused with this kilowatt per hour, kilowatt, right? Kilo is just 10 to the power of 3. Watt is the unit for power. Hour is the unit for time. In case you haven't realized, power times time gives us energy. So kilowatt per hour is just a unit to calculate energy. The reason why we don't do it in joules, which is the SI unit for energy, is because if we calculate energy consumption in joules, that number will be very big. It will be like a very big number. It's like almost like 1 kilowatt per hour is almost 3.6 megajoules, which is a very big number. So imagine your electricity bill come home and your electricity consumption is like millions. I was like, who can read that? There's so many zeros to go and count. So in order to simplify things, what we do instead is to calculate 1 unit of electricity as 1 kilowatt per hour. This means if the power rating is not in kilowatt, you will change it to kilowatt. If your timing is in seconds, minutes, or 1 day, convert it to hours. Because all you need to do after that is to take your kilowatt multiplied by the hour. You'll get how much electricity you consume in terms of kilowatt per hour. And of course, the one that consumes the most is the most expensive to operate. Okay, I'll give you 30 seconds to copy down. But I hope this point is clear. It's not a crazy concept. You just need to be very deliberate with taking care of your units. Okay, I hope you guys are following so far. Okay, remember at any point, if there's any questions, feel free to drop it in the chat. All right, this is meant for a session to help you. All right, so if you need clarity, let me know. Okay, I'll move on. Okay, next up, we have this situation whereby we have 3 resistors and 4 fuse. When the switch closes, which 2 fuse will blow? Okay, chill, listen first. Don't need copy yet, listen first. I'll give you time to copy. This is 110 volt. This is the EMF of my battery. One of the rules that we have learned is that if this is a parallel circuit, I call this I1, I2, I3. Lane 1, lane 2, lane 3. Every single branch will get 110 volt. Okay, because this is in parallel. So if my EMF is 110, every single branch is also 110. However, the resistance across each branch is different, 40, 30, 20. So naturally, even though the voltage is the same, because the resistance is different, we expect the current to be different. So current can be found by taking V over R. Okay, this is when you can start copying. Current in I1, voltage is 110, resistance is 40. Right, so current is 2.75. I2, you do the same working step. I3, you should also be able to find the individual current. So at this point, we haven't solved the question yet. This is just the current in each branch. So you now at least know how much is flowing through the 40 ohm, the 30 ohm, and the 20 ohm. The first thing I'd like to address is F1, which is fuse 1. Fuse 1's rating is 10 ampere. Now, because fuse 1 is part of the main circuit, where all the current has recombined back into the main river, the total current flows through F1, which means the current flowing through F1 is I1 plus I2 plus I3. So if I1 plus I2 plus I3, we add it up, you will see that the total number is clearly greater than 10, which means fuse 1 is expected to blow since the current exceeds the fuse rating. The other fuse that will blow is actually F4, which rating is 5 ampere, while the current I3 flowing through it is 5.5 ampere. Right? So did it exceed the fuse rating? Definitely. So F4 will blow. The one that I think is a bit more like not too certain is actually F2. Why do I say that? For those of you who are not clear, right, the total current flows in the yellow part, I1, 2, 3. But the moment it hits this juncture, I1 actually splits out. So the remaining current is I2 plus I3 that will actually flow through F2. And if you actually add up I2 and I3, it doesn't exceed the 10 ampere. So F2 will not blow. Once it hits this dot, I2 will go through F3, while I3 will go through F4. So I need you to be able to visualize how the current split, then how the current join back. All right. So the whole point of using the river analogy is to help you understand that the big river can split into smaller rivers, but the smaller rivers can also recombine back into the big river. Okay, so current, you need to be able to visualize it more so than just hardcore calculate. All right, that's for question 12. Moving on. Okay, next up for question 13. All right, so question 13, we have an electric iron here. We were told that this iron is used for 2 hours every day. They even tell us the cost of the electricity. So let's run through the statement one by one. Now, will the fuse melt? We are given power, which is 2.8 kilowatts. We're also given the voltage, 240. So if you actually take some time to go and calculate current, which is power over voltage, you will realize that the current is 11.67. Meanwhile, my fuse rating is more than that. So will the fuse melt? Nah, the fuse will not melt, right? Because the current is smaller than the fuse rating. Next, energy used per week. 2.8 is already in kilowatts. That's fantastic. 2 hours every day. So I'll take 2.8 times 2 hours is 5.6 kilowatt. But this is every day. Energy use here is per week. Okay, so we need to times 7. This statement here is factually true. So B is the answer. Meanwhile, the cost of using the electric iron per day is 5.6 kilowatt multiplied by the cost of the electricity. So how much does it cost to use it daily? Is about $1.40. So this statement here is not true. Meanwhile, for D, it is impossible to determine whether the efficiency is 100% or not. It's not possible to conclude. But in reality, nothing ever operates at 100% efficiency. Okay, there will always be some energy loss, meaning inefficiency in the system. Okay, so this is how you guys actually break down and solve question 13. Moving on. Okay, next up, test your deep understanding of your life, neutral, and earth. What I mean here is this. I hope you guys know by now that when we plug it into a socket, there are 3 parts, right? I mean the power plug, there's 3, right? The one that's actually bringing in the current is through the live wire. This live wire brings in the current at high voltage. All of this voltage is then like given to the light bulb, okay, or the component or whatever it is. Upon exit, there should be no more voltage, but there should still be current. Why? Because the river is still flowing. It's just whether the river has high voltage or not. So high voltage always before the component. After you exit, you usually have no voltage. So that's how we remember the difference between the live and the neutral wire. Current is the same because it's part of the same room. Meanwhile, your earth wire is the one that's connected directly to the metal casing of your appliance. Your earth wire itself will have no current and no potential. Why? Because it's not meant to be activated. It's there as a safety precaution. Earth wire will only activate in special circumstances, not normal. Special meaning if your live wire goes haywire and your live wire touches the metal casing, that is when your earth wire springs into action, right? As it will redirect the current to flow to earth instead. So your metal casing, instead of being live, instead of maybe causing people to get electrocuted, that current flows to earth instead and it gets discharged. Okay, so that's all for this question over here. Okay, why not A? The main difference here is A, right? The current is zero. Current is not zero because the current that flows out from the socket through the live still needs to return back via the neutral. Okay, so it's one big river where current throughout is constant. Okay, that's why option A is wrong. Okay, and lastly, question 15, another one to calculate the energy consumption. For this question itself, right, instead of saying that you do not know how to solve it, I want you guys to pay special attention to this. Okay, now, let me explain a bit further. Now, when we first read a question like that, let's just zoom out. And let's say we're just reading this question. The numbers that will always pop up to you is what? The 25 cents, 1 kilowatt per hour, 2.5 kilowatt, 10 watt, 4 hours. Why? Because you need to notice that these are all written in numerics. It's actual numbers. And when we do a question, right, we have a tendency to not read the whole question. We simply browse through. And it's very quick for our eyes to pick up numbers. Numbers. But take note, especially for practical electricity, there is this tendency for the question to write it not as the digit 2, but to spell it out as 2. So my worry here is this. I do not know whether it will apply to your WAs, but be very careful when doing practical electricity question, especially when you're calculating energy consumption. Because we're talking about 2 light bulbs. If you didn't see this 2 and you simply gloss over it and you say, oh, 10 watt, 4 hours, okay, I just take 0.01 kilowatt times 4, clearly your answer will be A. Right? You'll calculate less. Why? Because you ignored this 2. So all I'm telling you here is in advance, the careless mistake that you are about to make is not recognizing the alphabetical 2. Numerical 2 is not a problem. It's the alphabetical. Clear? All right. So I hope that this part is well taken care of. So for my students, you guys know this. I already told you already. It's not about, making careless mistakes. You should already know where your careless mistake will manifest. So you are really avoiding it in advance. Okay. Ivan, your quick question, why is voltage 0 at the neutral wire? Because all of that voltage, all of that EMF has already been given to the light bulb. So on the way back, there's no more voltage. Okay, live wire is bringing it there, so it's at high voltage. On the way back, no more. Okay, the analogy that I always give is imagine Grab food drivers. When they first deliver the food, there's a lot of food in their bag, right? So it's at high voltage, right? They're carrying a lot of food. After they deliver to the light bulb when they go home, the bag is empty. So there's 0 voltage. Can Okay, so when do you use watts? When do you use kilowatts? If it's in a chapter for practical electricity, especially for electricity consumption, that means how much electricity do we use is always in kilowatts. Watts is more for the chapter work, energy, power. That goes back to your way earlier. So in those questions where there's work done, energy, and time, then it's relevant. Okay, next up, quick one for question 16. Assuming we know that the LDR's resistance is 9,000, what's the total resistance? You simply apply the formula. I'll not explain this again because I went through earlier why I put to the power of -1 is the reciprocal. Meanwhile, the reading of the ammeter can also be found quite easily. So I'll give you about 30 seconds to work on your corrections before I move on. Okay, right. I think this one is not that difficult. We're just looking at a circuit in parallel. Okay, moving on. Okay, so we see that there's this very bright lamp placed near the LDR. Let's recall again. Bright lamp, LDR. Bright. Cave versus beach. Bright lamp, right? Bright. Resistance should decrease. So state and explain what happens to the ammeter reading when light intensity increases, resistance of the LDR decreases. So if the LDR resistance decrease, the effective resistance of the circuit will decrease. If resistance drop, current increases, your ammeter reading will increase. Okay, so you get 1 mark if you're able to state that ammeter reading increases. The second mark to explain must show the cause, what do you call it? Cash, okay, what, the cause and effect, I don't know, a causality or whatever. Basically, this one caused this one caused that one. So light increase cause resistance to decrease. If resistance of LDR decrease, your effective resistance decrease, which causes your current to increase. You get it? Like this causes that causes that. That's explain. It's a chain of event explanation. So if you miss out any like one part of the chain, then your explanation breaks down. Ken, still alive? So I sincerely hope that by going through this, you're able to apply to your WA2 and hence do better. All right. So I hope none of you are taking this as like, just listen, not important. No lah. Right. The very fact that you're here tells me you want to learn. So I'm doing my best to teach you as much as I can. But of course, limited scope lah. In our own classes, we spend about 2 weeks to go through DC circuits, but here I have like 1.5 hours. So I do the best I can. Okay, next up, let's take a look at question 17. So question 17, instead of going through the question, I'd like to spend one chance to talk about the question. And I mean by saying, how does this whole circuit work? Now, a lot of us might get very confused, but I'm going to show you the pathway of the current to help you understand what's actually going on. Now, take note that current always comes through the live wire, right? It passes through the main fuse box. Current goes in, passes through the main switch. Let's assume the main switch is closed. The first point it reaches, some of the current will branch out to the lighting circuit. If it's in yellow, this means that the current is still at high voltage. Now, where else does it go? It also continues down to go to the heater. It also splits up to go into the cooker. Okay, so far? Now, I want to zoom in on some very small parts here. I want you to notice that the parts where the current actually splits out, there is a dot here. The dot tells us that it's a node, meaning it's a point of connection. If you simply see two wires where it crosses, right, like this part here, it crosses one another without the dot, it actually means they are not connected to one another. So you don't be confused why this line cuts across so many lines, but it only goes to this point. The dot means it's attached to. If you don't see a dot, it means it's actually not connected. Some schools that are kinder will draw it like that. You'll draw the wire come here, jump over the other wire. You get it? It's like boing, it jumps over to show you that they're not touching. But most of the time, your teacher's lazy and they're just plotting the circuit. They will just draw a straight line, which is common practice, by the way. So don't be too shocked by this. Now, of course, if the current reaches the components, whether it's the lighting, the heater, or the cooker, it must find a way back. So let me show you the path of the way back. So the current will flow back via the neutral wire. It joins back to the main neutral, which is here, and then it comes home. At this point, the neutral is at low voltage. Same for the heater, goes into the heater, comes out via the neutral wire. Goes in via the live to the cooker, comes back via the neutral. So what I'm trying to show you all here is the path of the electricity going in through the live, carrying high voltage. This high voltage is then given to the components, right? So all that voltage, the potential difference when it comes out is zero. Still have current, still need to go home via the neutral, but now I'm at zero voltage. So state the function of the neutral wire. The function of the neutral wire allows current to return from the appliance back to the power supply. It's to complete the circuit because live brings it in, neutral brings it home. Okay, I know this might be a bad analogy, but just imagine soldiers going to war, right? They carry a lot of ammunition, right? So they go in via the live, they go and fight, right? They fight the light bulb, they go to the heater, they go to the cooker, they use up all their ammunition. The soldiers still need to come back home via the neutral wire. But when they come back home, they are at zero voltage. They have no more ammunition. Okay, there's probably a better example out there, but I hope you guys are getting the hang of things. Because ultimately, your current and your charges is like delivery service. It's just delivering the voltage to the components. On the way back, I'll still come back. Rate of flow of charges, the current still comes back, but I'll be out of my delivery item, which is the voltage. Okay, and the reason why the lights, instead of connecting both of them in series, they're connected in parallel, is because if one lamp blows, the other lamp can still continue to work. So that's the key advantage of a parallel circuit. Yeah, I'm going to give you more time, but question 17C, describe and explain how earthing the unit makes it safe. Take note, you only ever earth, right, if there is metal casing. You will see later on in the last question that I've selected, if there's no metal casing, you don't actually need to earth it. Why? Because if the live wire is somehow connected to the metal casing, maybe your dog go and chew the wire, then your live wire come up, then your live wire touch the metal casing. What the earth wire does is that it provides a path of low resistance and it directs the current away from the user, hence protecting the user. So if you notice, right, anything with 3-pin plug with the earth wire, it's usually because there's a metal casing. Most commonly for computers, I would say for kitchen appliances, they usually have an earth wire because there's quite a good chance that the casing is metallic. Okay, but if your casing is non-metallic, you do not need the earth wire. Okay, for those who are still around, I'm going to give you all one more big tip. If earth wire is activated, meaning like it comes into action, earth has low to no resistance. So if current flows to earth, right, and earth has very low resistance, which is why the current is directed that way in the first place, because very low resistance, current will greatly increase. Your fuse will melt. So typically, if the metal casing, live wire touches, earth wire comes into play, the subsequent thing that will happen is that your fuse will melt. So earlier in the class, I mentioned this idea, which is, it's not about fuse. I think everybody knows what a fuse is. The question is, do you know the situations that lead to the fuse melting? And I'm telling you the answer straight up now. There are two situations. Number one, if there's a short circuit, when your live wire touches your neutral wire directly, that causes the fuse to melt. Because you bypass the component, current will greatly increase, which means your fuse will melt. Second scenario that will cause the fuse to melt is when your earth wire itself is activated, meaning now current is directed to the earth, current will greatly increase, fuse will melt. So these are the two situations that typically cause the fuse to melt. Okay, the context of what happens before that leads to the fuse melting. Okay, last 10 seconds on this page before I move on. These are all actual prelim questions, by the way, in case you're wondering. So I didn't purposely choose easier or harder questions. These are just questions that exist. Okay, let's move on. Okay, so what is the maximum current that can flow in the live wire of the board mains fuse? We go back up quickly to take a look at the different fuse rating. This fuse rating is 5, 15, 30. So if this is 5, 15, 30, this means the main fuse must at least be an addition of the fuse, which is 50. Right, because each individual one you add up gives you the main one. Okay, which means a suitable fuse rating, typically, you want to increase it by 10 to 20%. So if your current here is like 50 ampere, the ideal fuse rating is closer to 55. But generally for schools, because the word here suggests, meaning it's quite open-ended, as long as you're giving a fuse rating that is higher than the current, they'll typically give you the mark. But if you're thinking, what is like this sweet spot for my fuse rating, 10% is good. Take note, fuse rating doesn't come with a decimal point as well. So you don't go and choose like, oh, imagine my current is 7, then my fuse rating is 7.7, cause just say 10%. No, if you want to choose, you choose like 8 or 9. Okay, because it needs to be a whole number. So that's for fuse rating. All right, next, question 17. This is the scenario that I was mentioning earlier when the live wire touches the neutral. Right, for me, this is your situation that we call the short circuit. It's a short circuit because now there's a shortcut that allows us to bypass the component. So short circuit will occur. They will all not work, right? Because now current doesn't pass through the components anymore. When that happens, effectively, your resistance drops to 0 because you have no more components. If resistance is therefore so low, the large current will cause the fuse to melt. But take note, because no current flows through the 5, 15, and 30 ampere, the fuse are not affected. Okay, and another easy device to replace the fuse is your circuit breaker. Okay, no rush. I'll give you a solid 1 to 2 minutes to work on your corrections. But I just need you all to be very clear about the two situations that will cause the fuse to melt. If your school didn't emphasize this, I'm sorry, but you learn it here. All right, Ken? So it's the situations that cause the fuse to melt that's important. Short circuit, earth wire activated. These two will cause your fuse to melt. Any questions at this point? Especially regarding either the short circuit or the earth wire, because these are very commonly tested when practical electricity is being discussed. For question 17F, will they ever ask why the circuit breaker can be resetted more conveniently? They won't ask you why. It's because the circuit breaker can be resetted. And I think the understanding will come in when we talk about the chapter in electromagnetism, as we understand the design features of a circuit breaker. The bad part about a fuse is that once fuse melts, you need to replace it. But a circuit breaker can be reset by pushing the button again. Okay, so imagine you're a house, for example, right? You don't want to use a fuse because it means what? If the fuse melt, you need to get an electrician down to change the fuse. Very troublesome. So instead, for houses and buildings, we typically see circuit breakers. It does serve the same function of protecting, but after everything is done, we can reset it. Okay, if not, let's move on to the final question in question 18. So this is the contrasting whereby there's only two wires. The wire that's missing is the earth wire. And the reason why we're able to only have two wires and that we do not need the earth wire is because of the word double insulated or doubly insulated, same thing. This means that the cable is insulated from the internal components. Furthermore, the outermost casing of the lamp is also made of plastic. So given that there's already two layers of protection, the likelihood of the live wire being exposed is extremely low, right? Which means we no longer have to worry about having to install an earth wire. So remember this, earth wire is only if there's a metal casing. If earth wire accidentally touches the neutral wire, it fundamentally doesn't change anything. It's just that now, if the metal casing becomes live, there's no protection. And yes, a circuit breaker is preferred rather than a fuse because it can be reset. Of course, it depends on what kind of circuits we are discussing here, but I'll say that in most household appliances, that would be the justification as to why it's better. Okay, 100 watts, 100 joules of energy is transferred from the chemical potential store to the internal store of the surrounding. Current in the lamp can be calculated by taking power over voltage. So 2-pin plug, double insulation. 3-pin plug, earth wire, metal casing. All right, last 20 seconds for those noting this down. I promise at the end of class to flash all the answers for the MCQ again for those who have missed it. So I will do so in a bit. Okay, and lastly, your fuse rating should be 1 ampere. Why? Because your current is 0.435. Remember, fuse rating is always a whole number. So don't tell me 0.5 ampere. No, that fuse rating doesn't exist. Okay, must be a whole number. All right, if not, as promised, I was going to flash the MCQ answers. So you guys can take a quick look, note down in case you missed out anything. All right, I'll just give you all 30 seconds here. Okay, I hope that the past 1.5 hours has been productive, right? Probably learned something new, okay, or at least had a good chance to recap many of these things that you might have forgotten. Okay, my sincere wish is that if you took time out to spend the 1.5 hours with me, I reciprocate lah by making sure your 1.5 hours is worthwhile. So I hope that this revision has been good. I think to wrap up today's class, I also wanted to share with you guys that there are other WA2 sessions ongoing for the other subject as well. So if you haven't yet registered for those, please do. I know a lot of you are currently slowly stepping down from your CCAs. And if you're thinking, hey, you might need some help, I'm not saying that you should or shouldn't, but if you feel like, hey, if this is the learning style that I like, whereby there's a lot of understanding and application and it suits your needs, do consider if you want to join the classes. For myself, I only take 2 physics classes, one at Jurong East on Thursday and Coven on Wednesday night. All right. So if the timing works out, you can consider. If not, you can also attend my other tutor sessions as well. Promise you it's just as good, just the same. All right. So other than that, I really don't have much else. I just really wish you guys all the best for your WA2. Let me know in the chat just how you found this session to be like, or if you have any last minute questions you'd like to clarify. But last but not least, thanks a lot for spending your Monday night with me. I will be uploading this recording onto YouTube in case you missed parts of it or some parts you'd like to rewind and look through. But ultimately, I hope that this has been a productive 1.5 hours with you guys. I did enjoy teaching you, but I hope you enjoyed learning as well. Let me know how you find it in the chat, and I'll end off the session here. Okay, bye everybody. Goodbye. All the best for WA2.